Hi, this lesson is about the laws or properties of logarithms. So there are three laws. The first one is called the power law, and the power law says that if you have the log base b of x to the n, that is equivalent to putting the n in front of the logarithm. So it's equivalent to n log base b of x. So it doesn't just have to be x, it could be something like log base 2 of 5 to the third power. That is equivalent to 3 log base 2 of 5. So it doesn't just apply to variables. The second one is the product law, which says log base b of x times y is the same as log base b of x plus the log base b of y. So a product of the log of a product becomes the sum of the logs of those factors. So again, it doesn't have to be variables. It could be numbers. It could be variables and numbers. So if I had log base 7 of, let's say, 2x, that would be log base 7 of 2 plus log base 7 of x. Okay. And then the last one is the quotient law. The quotient law says that if you have the log base b of x divided by y, so a quotient of two expressions, as long as that denominator is not 0, that is equivalent to the log base b of x minus the log base b of y. So the log of a quotient becomes the difference of logarithms. And again, that could be combination of numbers and or variables. So if I had, let's say 5 over, let's say the variable m, that would be the log base 3 of 5 minus the log base 3 of m. And again, that's as long as m is not equal to 0. All right, so we're going to use those laws in order to expand logarithms, and then we'll also use them to condense or express multiple logarithms into a single one. So we're either going to apply the laws in this direction, or we're going to go from the right to the left direction. We can also expand and simplify, and in order to simplify, these are helpful rules to know. First one says log base b of 1 is 0, and that's because b to the 0 power is 1. Remember, every log can get rewritten as an exponential expression, and so understanding them as exponentials makes it a little easier to understand the logarithm. The second one is log base b of b is 1, and that's because b to the first power is b. And the third one is log base b of b to the n is n, and that's because b to the n equals b to the n, which is what I wrote here. All right, so let's practice using some of this information. Here, for number 1, I want to expand log base 3 of 14, right? So it appears there isn't much to do here, but 14 can get rewritten as a product. So I rewrote 14 as 2 times 7. So that's equal to log base 3 of 2 plus log base 3 of 7 when you apply the product law. All right, then we go on to another example. I have log base 8 of n to the 5th. Here I'm using the power law because the exponent 5 can get written in front of the logarithm. So it's 5 log base 8 of n. So that's an example of using the power law. In this next example, we're going to be using more than one law. I'm going to use both the power law as well as the quotient law. So I want it to be visible up there. So because I have a quotient of expressions here, but this cube root of y can get rewritten as y to the 1/3. So I'm going to use the power law on that top part. So when I expand this, this will be 1/3 log base 3 of y minus log base 3 of 7. Okay, so let's move on. This is another example of where we're going to be using more than one law. In fact, we're going to use all three of them. I have a product on top. I have a quotient over all, and the denominator has an exponent. So you're going to use product law, quotient law, and the power law. So when I expand the numerator, log base 2 of x plus y, that's where the x times y gets expanded. And then the denominator z cubed becomes minus 3 log base 2 of z. So the 3, the exponent becomes the coefficient, and you subtract out that logarithm because of the quotient. All right, here's another one. This time we're only using one law, but it's another radical. And remember, with radicals, you have to rewrite them. This is log base 4 of the 7th root of x. So this is a root, not a coefficient. That's rewritten as log base 4 of x to the 1/7. But then the power law says that the 1/7 goes in front. So you end up with 1/7 log base 4 of x. All right, in this next example, we are going to both expand and simplify. So I have log base 2 of 32x to the 2nd power. So I have to use both the product law and the rule for exponents, but I'm also going to be able to simplify this. So using the product law, this becomes log base 2 of 32 plus log base 2 of x squared. Now I still have to put this 2 in front because of the power law, but notice that 32 can be rewritten with a base of 2. And when that happens, you can actually simplify it because my base for my logarithm is 2. So 32 is 2 to the 5th power. So log base 2 of 2 to the 5th is just 2. It's just 5. And that goes back to what I wrote here. It's just going to be the exponent when the base of your log and the base of your expression are the same. You just get the exponent. So that's what we have in this example. Log base 2 of 2 to the 5th is just 5. And the second expression just becomes 2 log base 2 of x. And there's a plus sign there. All right, so here we have to condense. Condense means you're going in the opposite direction. You're taking the expanded logarithms and writing it as a single logarithm. So how do we get from this to this quotient here? And that's because I have a negative in front of the first one. Remember, if I just reordered this, this is the same as log base b of v minus log base b of capital R. So when you see it like this, you're clearly using the quotient law in order to compress it, and you get log base b of v divided by R. So you need to be able to think that through in order to use the appropriate log law. All right, so here's another one where we want to condense this as much as possible. So I did a couple of things. So I have log base 4 of 3 to the 3rd plus log base 4 of 9. So you're definitely going to be multiplying the 3 to the 3rd and the 9, but I rewrote the 9 as 3 squared because then it would be easier to combine the 3's. So when I rewrite it using the log law, it's log base 4 of 3 cubed times 3 squared. So the sum becomes a product, but you can add your exponents so you get log base 4 of 3 to the 5th. And if you multiply 3 5 times, it's log base 4 of 243. So here's another one where we want to condense or compress this. I'm going to be using more than one law. I'm going to be using the one for product because I have a sum, and the one for the power law because I have a coefficient in front of that second one. So first thing I did was I moved that coefficient and it became the exponent of the second logarithm. And then here I rewrote this as a square root, but you can actually do a little more. So the next step is to then combine these two using the product law. And with the product law, you would get log base 2 of 3 root x. Okay, here's another one where we're using more than one law. I'm going to be using the power law because I have another coefficient here. I have another one for the second logarithm. I'm also going to use the quotient law. Oh, I think I did a typo here. This one should be a 3. I'm also going to use the quotient law on this because I have a difference. Okay, so this is 1/3 log base b of a minus 2 log base b of 5. So there's my problem rewritten. First thing I did was I moved my exponents to my coefficients to the exponent position. So that's what you see in the next line. Log base b of a to the 1/3 minus log base b of 5 squared. And when you put that all together and condense it, it becomes a quotient. And this a to the 1/3 is the same as a cube root of a. So you get log base b of cube root of a over 25 because 5 squared is 25. All right, so here we want to simplify, and we did this a different way a few sections ago, but now that we know our log laws, it might actually make it a little easier. So first thing I did was I rewrote log base 3 of 1 over 81 into log base 3 of 1 minus log base 3 of 81 using my quotient law. But if you recall, log base 3 of 1 or log of any base of 1 will always equal 0. So that part simplifies pretty quickly. And 81 can get rewritten with a base of 3. So this is 3 to the 4th. So again, using that other rule, this is just equal to a minus 4. So your answer is just -4. And that's because, and again, just thinking it through in terms of exponentials, that's because 3 to the -4 power equals 1 over 3 to the 4th, which is 1 over 81, which is what we were taking the log of. So here's another one. I have log base 5 of 5 to the 0.1. So that's again using the same rule that we used here. When your base is the same for your logarithm and your exponential expression, base 5, it's just the exponent. So the answer is 0.1. So again, this one is similar. So I have log base 6 of the cube root of 6. So I used my power law to write this as 1/3 log base 6 of 6. But log base 6 of 6 equals 1. Again, that's one of the rules I gave you above. And so your answer is just 1/3. So these can, oftentimes with logarithms, you have more than one option in order to simplify. We can also use logarithms to calculate very large numbers or very, very small numbers. So that's like a practical reason to use logarithms. So suppose we wanted to evaluate 895 over 73.4 to the 86th power. So if you actually entered this into a calculator, you might get some sort of error message or like overflow because this denominator is a very large number, making the number overall, this whole fraction would be then a very small number. So any number divided by a very large number becomes a very small number. So what do? We take our fraction, and I'm going to let n equal that fraction. Then I've created an equation, and so I'm going to use common logs. to help me evaluate this. So I'm going to take the log of both sides. So log of n equals log of 895 over 73.4 to the 86th power. But here, from here to there, I use the log laws. So I wrote it as a difference because of the quotient law. And I also put this exponent in front. So it's log 895 minus 86 log of 73.4. Okay, so now this is more manageable. You can put this line into a calculator and you would get an answer of negative 157.49803881. But that's not the value of this. That's the value of the log of that number. So I still have to figure out what n is. Remember, n is the fraction that we're interested in. So that means that n will equal, remember that's what we call the anti-logarithm, n would then equal 10 to this power, which again might not be very practical to put into a calculator, but you can split up this 10 to the negative 157.49803881 into 10 to the negative 157 times 10 to the negative, and there's that decimal part, because when you're multiplying, you can actually add your exponents. And if I were to add negative 157 and this number here, I would get the negative 157 that you see, 0.49803881 that you see above. Using scientific notation, this number becomes 3.15 times 10 to the negative 157. Remember, that means that the decimal gets moved 157 positions to the left, which is definitely not practical to do. So using scientific notation, we get an answer. All right, here's another one. We want to use logarithms to evaluate this number. This one is the opposite of the previous one in that in this case, this will be a very large number, because notice that on top, I'm taking 126,000 and raising it to the 20th power. And then my denominator is a much smaller number. It's 2.63 raised to the 2.5 power. All right, so again, if you put this directly into a calculator, you'd probably get some sort of error or overflow message. So I'm going to use logarithms. So I take the common log of both sides. On the right side, you can rewrite this as a quotient. The quotient as a difference, and put my exponents in front as coefficients. So you get 20 log of 126,000 minus 2.5 log of 2.63, which gives you this as an answer using a calculator, 100.9575215. All right, then we let n equal 10 to that value that you just found. But again, I'm going to use what I know about scientific notation in order to break this down, and using what you know about exponents. So the 10 to that power can get rewritten as 10 to the 100 times 10 to the 0.9575215, because 100 plus that number gives you the exponent above. Okay, but 10, this number, 10 to the 0.9575215, is 9.07 times 10 to the 100th. Again, leaving that in scientific notation, what that means is that you would have to move this decimal place 100 units to the right to get the actual number. So it's clearly a very large number. Okay, so as we've talked about in the past, your calculator has something called a common logarithm, which is expressed as log, and a natural logarithm, which is expressed as ln. But if you need to evaluate a logarithm with a different base, your calculator is not capable of doing that. So we have something called a change of base formula, which allows you to take the logarithm of any base and convert it to another base. And the base that we would want to use would be either base 10, which is the log, the common log, or base e, which is the natural log. So if you have log base b of x, that is equal to log base a of x divided by log base a of b, where a is your different base. All right, so how are we going to use this to help us evaluate expressions? So we're going to use the change of base formula to evaluate log base 2 of 17, and we'll round to the thousands place. All right, so as I said, there's no way to break down the 17 into a base of 2, so I really can't do this without using technology. But again, calculators do not have base 2, but they have base 10 or base e. So according to the rule above, I'm going to change my base 2 into, and I'll pick base 10. I'm going to rewrite this as log base 10 of 17 divided by log base 10 of 2. Notice that in the denominator, you're taking the log of whatever your base was. So that's why we have 2 there. This is something you can input to a calculator directly, and you get 4.087. Another option, which would give you the same result, would be to use the natural log. And if you're using the natural log, you're just doing ln of 17 divided by ln of 2, and you also get the same answer. So it doesn't matter which one you use, but you have to use either common log or natural log. So here we will again try this again using both, showing you that you get the same results. So here I want to compare the calculation of the natural log of 0.5017 to the calculation using the common logarithm in the change of base formula. So I'm going to rewrite my natural log in terms of a common log and see if I get the same value. So if you put this directly into a calculator, ln of 0.5017, you get negative 0.6898. But converting it to a common log means that I take the common log of 0.5017 divided by the common log of e, because the base of the base of ln is e. Remember, in the denominator, you take the log of that base. So here the base is e, you just don't write it out with common logs. So if you compute that quotient, you get the same answer. All right, so here we're going to use the change of base formula to evaluate the log base 12 of 122, rounded to the thousands place. Again, it doesn't matter if you convert it to a common log or a natural log. This time I chose a natural log. So log base 12 of 122 is the same as the natural log of 122 divided by the natural log of 12, and that is approximately 1.933. All right, so now we're going to graph these. So I'm going to use a graphing calculator, and if you don't have a graphing calculator, any app will do. I often use this one. You can either go to their website, desmos.com, or download the app, and it will allow you to graph this. So if you can't put it like this into a graphing calculator because, again, we don't have a base 8. So in order to view this, you would have to rewrite it in a different way, either in terms of common logs or natural logs. So 2 log base 8 of x, you're basically just rewriting log base 8 of x, and 2 becomes the coefficient. So that's ln of x over ln of 8, or it'll be 2 log of x over log of 8, and you would get the same graph. So if you were to put that into a graphing calculator or an app, you would get this as your graph, which is a picture that we've seen before because we've graphed logarithms before. Remember, just as a reminder, this means that your domain is all positive real numbers, and the range is from negative infinity to infinity. Okay, so now let's do a comparison. If we use a graphing calculator to graph this, and we don't have to do a change of base because it's a common log, I have y equals log of x squared divided by log of 8. All right, so when you graph it, you notice that you have a graph on either side of the y-axis, and that's because of the x squared. I'm no longer restricted to only using positive values of x, because when you square a negative number, you get a positive result. So that's why you have part of the graph on the left side of the x-axis and a part of the graph on the right side. So the whole thing represents this function. But then if I compare it to what I just did above, this was the one we just graphed before this one. My graph looks like only part of this. But notice that the log of x squared, according to the laws, I can't put the 2 in front and get log of x. So technically they should be equivalent, but it actually does change the graph because it changes the domain. All right, so let's try to understand this a little better. Explain why the graphs of y equal to log of x squared divided by log of 8 and y equal to 2 log of x over log of 8 are different, even though the laws say that these two would be equivalent. Well, in the first one, your domain is all real numbers except 0, because when you plug in a negative number and you square it, you get a positive result. But for the second one, your domain is only positive real numbers, because remember, the log of 0 and the log of negative numbers does not exist. So that's why for the second graph, you're only on the right side of the y-axis. Okay, so that's it for this lesson. Give the homework a try. Good luck.